Okay, so last time we discussed the page curve, plotting the entropy of an evaporating black hole. The green curve is what you get from Hawking's calculation, that is from a thermal gas. And that's a problem. The area is the area over 4 of the black hole, which is what we think is the entropy. And the red curve is the unitary page curve. That's the answer that we expect or would like to get if black hole evaporation is actually unitary. Now, the next thing I want to explain is that this problem that we've identified here, the problem being the difference between Hawking's answer for the entropy and Page's answer for the entropy, this is very robust, okay? And I would say it's been known for a long time that any small, perturbative effects cannot help you. Okay, so of course, none of these calculations are done exactly. Hawking's calculation makes various approximations, but we'd like to understand whether the conclusion is robust to these approximations. And the cleanest way to say this is a theorem of Mator, which I'll first, I'll say this sort of informally, but then we'll see what I mean by it. So the theorem basically says that small local corrections to Hawking's calculation cannot fix the entropy. And we're going to make this argument just using quantum info inequalities. So there's hardly anything that goes into this argument, hardly anything. And that's what makes it so robust and what makes this problem so difficult. So here's the proof. Before we get into the real part of the proof, I need to say a few words about strong subadditivity, which I wrote up before. So let me first remind you what I wrote before. So if we have a Hilbert space that separates into 3 parts, so just think you have an A, a B, and a C that all factorize, then strong subadditivity says that S of AB plus SBC is greater than or equal to SB plus SABC. But we actually don't want strong subadditivity in this form. We want a different version. So the equivalent version of SSA that we're going to use says that SAB plus SBC is greater than or equal to SA plus SC. And I'm going to prove in a second that that's not obviously equivalent. But I'm going to prove in a second that it follows from the first version. So let's derive this other version of SSA. I'm going to start with the ordinary SSA inequality, but put primes on everything because we need to, well, they're going to end up with different names. So start with ordinary SSA for a system with pieces A prime, B prime, and C prime. We can always purify the system, the combined system with these 3 parts by adding another piece. So I'm going to think of this as being A prime, B prime, C prime, D prime, where the full state is on the, so the state on ABC, on A prime, B prime, C prime, D prime, we can now assume to be pure. Okay, so SSA in its original form says S A prime B prime plus S B prime C prime is greater than or equal to S B prime plus S A prime B prime C prime. And now I'm going to trade this and this for their complements. Okay, so since the whole system is now pure, S A prime B prime is the same as S C prime D prime. Okay, so I trade this one for its complement. S B prime C prime we'll just leave alone. Sorry, I marked the wrong one. It was the second, that one we're going to leave alone, S B prime. And this last one we trade for its complement, which is S D prime. And then we just relabel things. So if we call this one A, B, C, then we've now derived the formula that's this SSA in the other form written on the other board. Is that clear? Okay, so we're now going to apply this to the black hole. And the let's see. Okay, so we have a black hole that's evaporating. So the space-time looks like this. There's the event horizon, and we choose a slice that goes inside the black hole like that. And then we're going to divide it. We're going to divide, well, we're going to choose 3 regions, which are like this: A, B, and C. So you should think of those B and C as being very close to the horizon in the region where most of the Hawking radiation comes from. Now what we're going to do is try to break strong subadditivity. Okay, so let's think about the escape of the Hawking radiation. So the Hawking radiation is a mode that starts out near the horizon in region B, and then it escapes into region A. You have to think of these regions as being time dependent. Okay, so region B at early times has some particles in it that escape into region A at late times. Okay, so if a particle escapes into the Hawking radiation, then SA at time t plus delta t is SAB at time t, because if the particle moved from, so if the particle moves from region B into region A, then the entanglement entropy in region A, now you also have that particle. Okay, so it's just SAB from a moment earlier. If we assume unitarity, then this is less than or equal to SA of t. For t greater than the page time t page. Okay, so the page time is when the curve turns over. If you want that curve to go back down to 0, then eventually it has to be decreasing. So all we've assumed here is that the curve is eventually decreasing, and then we've focused on the emission of one Hawking quantum during the stage of evaporation where the curve is on the downslope.
Could you say again how we know that SA of t plus delta t is SAB? And why is there no delta t dependence on the right-hand side of that equation?
Just think of this as this delta t. So t is before this particular particle moved from B into A, and t plus delta t is a little bit later after that particle moved from B into A.
Is there one particle in region B at time t?
Well, there could be many. Oh, sorry. Yeah, we're only keeping track of one of them. That's right. So I guess I should go back a second. Okay, so remember when we talked about the fine-grained entropy of a region, we said that it includes two pieces. It includes the entanglement of the actual stuff, like the particles that are there, and it includes the vacuum entanglement at the edge. And this argument is being made in sort of a toy model where you only think about the stuff. Okay, so if we really tried to make this argument, we'd have to be more careful about the UV divergences at the edges and that sort of stuff, and the extra particles that, like you're talking about, the extra particles in region B that haven't escaped yet. Think of this as just being in the sort of qubit model where there's one particle in region B that hasn't escaped yet. Yeah.
Does it matter here that B is outside the horizon? Is it really outside the horizon?
Yes. Well, it doesn't yet, but it's about to matter.
Okay.
Yeah.
I mean, since that particle is anyway not escaping from, like, it's only moving from B to A, right? So if you consider the entire system AB, so that entropy should not change.
Right.
So SAB of t plus delta t is also equal to SAB of t.
Agreed.
Then I thought that is what you were trying to tell. I didn't understand why SA of t plus delta t is equal to SA.
Okay, region B is just big enough to contain this particle that hasn't escaped yet.
Oh.
It's just big enough to contain that particle plus region A.
Okay.
Is there another question?
This is like a very classical way of thinking about it. Like
It is. That's true. Yeah. I think you could probably make this argument more quantum mechanically. In other words, keeping track of all the UV divergences in these entropies. Although I don't think I've seen anyone actually do that carefully. I don't think it would make a difference. Because basically because all those contributions would be constant in time, I think, at least over the Yeah, I think those contributions would be constant in time, and you could subtract that out. But I agree. I'm making a sort of a. This is sort of a toy model argument, but I think the argument really does apply to real black holes because just because I think you could subtract those terms out. I haven't seen someone do the calculation carefully that way though.
Yeah, it's also like assuming that there are a definite number of particles in region B.
Yeah, I agree. I agree. It's too much of a toy model and it's too classical, but I think it's correct. So let me make it a little better. It's a little better than what I just said. So this is a free field that we're talking about in curved space, and if we focus on a particular mode of the free field, say the one that's around the Hawking temperature, the one that's likely to be emitted, then you can write the quantum state in this region, and you can ask whether it has particles or not yeah, I think that's actually totally well defined. We could just think about the A's and A daggers of this quantum field, and we could ask whether there's a particle, and I think it's fine.
An eigenstate of particle number.
No, but we could ask the expectation value of the particle number.
But your argument was based on there being like one particle in region B.
Yeah, we'd have to be more careful. I agree. Yeah. But I don't think it would be that hard. So that's why I think it's still right. Okay, so smoothness of the horizon is the second input to this. Smoothness is going to tell us that SBC is less than SB, which is comparable to SC. Okay, so again, we're thinking about a situation where there's some particle here that's escaping, and it's entangled with a particle in region C inside the black hole, just on the other side of the horizon. Okay, so the fact that this particle is entangled with its partner here tells you that SBC is less than SB. The fact that these are equal, that's just because, well, you have one of these on each side. So in a more quantum-y kind of way, the quantum state on BC is going to be well approximated by thermal field double, that we discussed a few weeks ago. So the thermal field double is exponential of minus integral d omega e to the minus beta omega over 2, a dagger omega, a tilde dagger omega acting on 0, where you should think of this inside being a tilde dagger, the particle that's created by a tilde dagger omega, and the outside is the one that's created by a dagger omega. Okay, so the thermal field double state, when expressed on top of the vacuum with respect to Schwarzschild time, really does have particles. These are the particles. Okay, so when we talk about it having a particle in there, we're just talking about being in this entangled quantum state. So that's actually accurate. So we're almost there.
Is this argument valid at all times?
Sorry?
Is this argument valid at all times, or this?
Which part of the argument?
So the second part.
Yes, I think so.
I mean, even when the number of degrees of freedom in the black hole are insufficient for the radiation offset to be entangled.
Yeah, because this is just a statement about quantum field theory in curved space.
I see.
The smoothness of the horizon requires those quantum fields to be in this entangled state. So, yeah.
I see.
Okay, so unitarity told us that SAB is less than SA. Smoothness told us that SBC is less than SB, which is comparable to SC. And together, this contradicts Strong's additivity. Okay, so Strong's additivity in the way that we had it when we write it again was SAB plus SBC is greater than or equal to SA plus SC. But this is less than that, and this is less than that. Not going to work. Yeah.
So the fact that it's the thermal field double state, not just any pure state, that's just this is not an assumption, right? This is like definitely the case.
Yeah, that's not, well, it's an assumption. It's the assumption. It's the equivalence principle. It's the assumption that GR and quantum field theory and curved space are correct. So it's not much of an assumption.
But so the moment you assume a smooth horizon, this is sort of enforced on you. You can't have any other pure
Yeah, that's really, I guess what I mean by smooth horizon is that it's a locally flat region of space-time where an inertial observer won't see anything interesting happen. Okay, so what this proof has really formalized is something that's called the monogamy of entanglement, which I mentioned earlier. Which is just saying that a particle can't be highly entangled with two other, like if a particle is if A is highly entangled, let me say it in the context of the black hole. The question is, who is this particle here entangled with? Smoothness of the horizon tells you that that particle has to be highly entangled with its partner behind the horizon. But monogamy, which is strong, which we could think of as this strong subadditivity inequality in this context, says that if it's highly entangled with its partner behind the horizon, it cannot also be highly entangled with the Hawking radiation that's already escaped, the early Hawking radiation. Okay, but that's exactly what you would need for the page curve to go down. What you would need for the page curve to go down is that this radiation coming out at late times is entangled with the radiation that came out at early times, because then when this new particle came out, it would make the state more pure, and the entropy would go down. Okay, but monogamy is not letting that happen. It's not allowed to be entangled with both. Escaping particle cannot be highly entangled with both interior partner and the earlier radiation. And as I said, it's nice to say it this way because this is really very robust to any changes you would make to this calculation. You know, when I talked about the quantum state BC, I said it was approximately thermal field double. But anything that's at all like this, at all like the thermal field double, is going to have the same problem. So it's not like you can, you know, the Hawking's calculation was missing loop corrections. It was missing the back reaction of the quantum fields on the geometry at intermediate steps. It was missing, who knows, maybe there's like some new particle that hasn't been discovered at the LHC yet, and that particle could modify the Hawking rate a little bit. There's all sorts of stuff missing from this calculation. Maybe we even change the laws of physics a little bit. Like, you could take quantum field theory, you could take the Hamiltonian of the standard model of particle physics and just like start sprinkling in new terms around the Hamiltonian. But unless you drastically change the entanglement structure of the quantum state at the horizon, you're not gonna solve the problem. You're not gonna change the fact that the page curve is off by a huge amount at the end of the calculation. The best you're gonna be able to do is maybe make it like, if you have some small corrections, then you can, well, I won't try to make a plot, but if you have small corrections to the Hamiltonian, then maybe you can get the curve to go down by epsilon. But you're not going to get it to turn over and come all the way down. Okay. So, like I said, I think this was roughly known for a long time. You know, if the calculation had been sensitive to the 12 loop correction, it never would have been called a paradox in the first place. I mean, that was the whole reason it was considered a hard problem. But this very robust way of thinking about it is more recent. That was due to Mator, and it was popularized and reapplied with a paper that introduced what's called the Firewall paradox, or the AMPS paradox after its authors. Which I've basically already stated the Firewall paradox, but let me just recap so I can put it all in one place. The Firewall paradox is the following. If the page curve decreases, this means that A and B are highly entangled. And this means that B and C are not highly entangled. And this means that the state at the horizon does not look empty. To somebody who's falling through the horizon. That's why they call it the firewall. It's a tension between various things, but one way of saying it is that if black hole evaporation is unitary, then you go through this logic, and there cannot be sufficient entanglement across the horizon for the state to be smooth. So if you jump in, you're going to hit a firewall. That's how they said it. So let's kind of see where we are. And I think all these paradoxes are just other ways of looking at the information paradox that was already discussed and understood very well by Hawking. So the information paradox, I don't like the word paradox. I use it because that's what everyone else uses. It's not really a paradox. Of course, no paradox is really a paradox if you if you look at it closely enough. But it's a puzzle, and it is a tension between three of our favorite things in physics: unitarity, or unitary quantum mechanics. Number two, effective field theory, or the idea that when you're working at the kilometer scale, like we are near the horizon of a black hole, that you shouldn't have to know the theory of quantum gravity. When you're working at the kilometer scale, you should be able to use the effective field theory that's appropriate at the kilometer scale, and that has black hole solutions that are completely well controlled. We should be able to talk about black holes. And locality. There are various proposed resolutions. All of them do away with one of these one way or another. Okay, and exactly how you do away with it, well, there are more acceptable and less acceptable ways to modify these things. But let me give some flavor for the kind of things that people have done for the first two, and then we're going to focus on the third. So, unitary quantum mechanics. Well, you could try to throw out quantum mechanics, but quantum mechanics is extremely rigid. It's extremely difficult to modify quantum mechanics and get anything that makes any sense at all. One thing you can do, which seems less bad, is you can just declare the universe to act like an open system. Okay, so it could just be that the interior of the black hole just kind of separates off from our universe. It's sitting somewhere else in some abstract sense, elsewhere, but we're still entangled with it, and so that the universe that we observe acts like an open quantum system. I think that's logically fine. There's nothing terrible about this proposal, but it has some issues. So there's nothing terrible with changing in the sense that we're not breaking quantum mechanics. It's just the quantum mechanics of an open system. What's wrong with it is that it really makes it hard to understand why black holes have any kind of thermodynamic interpretation. Remember that the page curve was a problem that came in much earlier. We didn't have to wait until the black hole was gone to see a problem with the page curve. If you think that the entropy of a black hole is the area over 4, then you have a problem much earlier. Okay, so these proposals that violate number 1, they also kind of do away with the idea that black holes have entropy equal to area. Not kind of, they do away with this. You cannot have entropy equal to area in this situation. There's another, and these are, most of the ideas in this category are what I would consider remnants. A remnant is like a little piece of space-time that is either left over or breaks off, and we remain entangled with it at late times or forever. The other problem is that these remnants have to be very tiny objects with an enormous amount of entropy, and that causes problems when you try to think about how that interacts with the world. So, like, for example, can these remnants run in loops in quantum field theory? Well, if so, there's an awful lot of them. There's an infinite number of them at finite energy. So I don't really know how to do quantum field theory anymore if you tell me there are remnants in the world. I don't really know how to do thermodynamics anymore if you tell me there are infinite entropy objects with finite energy. That just seems really weird. Okay, moving on to the second one, violations of effective field theory. what do I want to say about this one? Well, there's a proposal called the fuzzball proposal, which is the idea that in string theory, there are some solutions that are not black holes. So like, they have the same mass as a black hole. They have the same angular momentum, maybe, or charge as a black hole, but they're not black holes. If you go up near where you felt the horizon, if you stand far away, they look like a black hole. But as you get up close, some much more complicated solution made of stuff, string theory stuff. And there's a proposal that that basically you should think of those as being the true solutions. And then black holes are not really relevant anymore, so you're okay. You now have, instead of having a black hole, which has this featureless, smooth horizon, you have something built of all sorts of microscopic junk, and then you don't have a paradox. Okay, it's like a star. A star doesn't have an information paradox. At the surface of a star, there's a very complicated quantum state of the particles that make up the star. That quantum state has all sorts of correlations in it, and when it emits radiation, it emits it in a correlated way, and there's just no paradox there, because the structure of the surface of the star allows the state to not be anything like the thermofield double state. So then you've escaped the problem. However, you've thrown out black holes, okay? You haven't really solved the problem at all. You've just said, well, I don't like black holes, I like these other solutions, and if I talk about the other solutions, I don't have a problem. So then you have to explain if those are really the important solutions, then what the heck's a black hole? Okay, and that circle has not been closed in this discussion. Now, there are proposals that maybe you could get black holes in some effective way, but I don't think there's a really compelling way to make this work beyond some very special examples in highly supersymmetric situations in string theory. Yeah.
So it can't be that the remnants are in the baby universe in some sense, and so then you wouldn't have to worry about them running in loops in this universe.
I don't know. Maybe. Yeah. There's a question of whether the remnants can interact with our universe in any way. You know, maybe there's a rule that like remnants aren't allowed to run in loops or something. I don't know. I don't know whether I'm not aware of anyone ever like writing down a theory that makes sense that you can do calculations with that tells me how to include remnants in a loop. I'd be happier if there was a calculation and I could see like, oh, the remnants like drop out or something. There's nothing like that, as far as I know. Yeah.
So you've made these first two possible solutions sound fairly implausible. I'm wondering if that's like your own personal bias, whether there are other like serious professors who would like, or proponents of these ideas and who would like give them like strong defenses.
I would say yes. It's a feature of my bias. I mean, I'm not like alone in having this bias, but the ones I'm mentioning are the serious ones. Okay, the idea that black hole evaporation is just not unitary, and that we should think of it more like an open system. This is something Hawking advocated for decades. A lot of people in the GR community still advocate this. Wald and Unruh, I think, are still very much in this camp. There's sort of a divide, like around here. There's sort of a divide between people who have more of a string theory and quantum field theory kind of background and are unwilling to change quantum mechanics for that reason, and people who have more of a general relativity type background. Okay, so there's certainly serious people who are here. There's a small but serious camp of people who are advocating for this fuzzball picture. I think they have some toy models which are nice and illustrate the idea that they're advocating. My personal bias, I suppose I could say, is that there's not a compelling argument that this is actually how it works. That they're toy models which have these sort of more complicated solutions. There's not a great argument that that's really how it works with black holes. They have some solutions that they found, but okay, I'm not convinced that that's the mechanism. But they're all serious. I don't think it's settled. I don't think that. I don't think we know the answer.
But like, given what you said in the colloquium that you gave, it sounds like you're pretty close to having resolved it by like slightly highlighting locality. And
well,
why aren't the people in those other camps moved by that?
Yeah. Let's see if I can answer that. Okay, let me say two things. First of all, I think the reason is that none of us have a completely compelling. None of the categories has a completely compelling story for how it works for actual black holes. You know, what I think I just said, like, they have these toy models, but I'm not convinced it's, or like, let's take, my objection to this one was that, well, I'm not sure how these remnants interact with matter, and I'm uncomfortable with that one. They would say, well, so what? Like, that's, you know, we could, just because we don't have a complete understanding of these remnants doesn't mean they couldn't exist. Like, just because you don't understand them doesn't mean they're wrong. And that's a perfectly valid counterpoint. In this case, I said, I'm not convinced that the toy models are the way it works for actual black holes. I think that some of these people would say the same thing about the toy models that support option 3 that we're coming to in a minute. The support for this one comes from string theory, ADS-CFT, and the kind of wormhole effects that I talked about in the colloquium, and we'll talk about more. But they would say, oh, you're using ADS-CFT, like that's just some toy model. It's not a real black hole. Or they could say, you're using the Euclidean path integral, the Euclidean gravitational path integral, and we don't even know if that makes sense. We don't know if the Euclidean gravitational path integral is well defined, so why should I care about your toy model? I think all of these are valid objections, and we don't know the answer. We have various arguments. I think the way I think about the arguments for option 3, which we haven't gotten to yet, are that they're not really proving it's correct. They're just showing us how it would work if it's unitary, and how it can work without breaking anything else that we know. But let me say option 3, because I don't want to have for too long on the board the idea that quantum gravity is not local. No, that I don't want to give that impression. But so let's think about this one. 1 second. So the third basic principle that I said maybe we need to violate or modify a little bit somehow is locality. But let's stare at this one for a minute, because what does locality really mean in quantum gravity? What is locality in quantum gravity? How can you violate it if you don't know what it is? Okay, because locality is a statement about geometries and like light cones in a geometry. And quantum gravity is not really a theory of, well, it's certainly not a theory of classical geometry, and it's not even really a theory of geometry in the way we usually think about geometry. Okay, so it's not clear that locality ever should have been on the list as a fundamental principle. I mean, of course, we need to have a theory of quantum gravity that respects everything we know about locality at low energies. That's absolutely needs to be on the list. But if black hole evaporation is unitary, it really has to be non-local in some mild sense. Because if you think about the Penrose diagram, you've got stuff in here, and you need it to get out here. Okay, those are not causally connected. So the whole point is to look for something that doesn't respect causality of the semi-classical space-time. And the question is whether that's a problem, and I think the answer is no. I think that quantum gravity can be a little bit non-local. And as long as it doesn't happen in a way that lets you like send signals faster than light or other crazy things like that, that we can easily see are false at low energies, then it's not necessarily a problem. So I don't even really think of my preferred resolution as being a violation of locality. I think of it more as just being a clarification of what it means for a theory of quantum gravity to be local or not local. Because when we talk about perturbative effects in quantum gravity, we know what it means to be local. It just means that you can't escape your light cone. But when we talk about non-perturbative effects, what does that mean? The contribution of non-perturbative effects can be effects where like this geometry tunnels to a totally different geometry, and who knows what the light cone is then when you allow stuff like that. Okay. Yeah.
Okay, so barring actually going to a real black hole and measuring any of this stuff, what would you think would be a theoretical like lowest bar for resolving one, if not at least one, if not any of these objections that you have written up on the board? Like what sort of theoretical calculation would resolve the arguments that one or not, if not all, the camps would?
You mean a calculation that everyone would agree with?
Or that at least eliminate one of the groups that would convince one of the groups. I don't know about the fuzzball people, but at least maybe the top one.
I don't know. I mean, I think it's even possible that these are all theoretically viable, and that choosing among them is an experimental question, or phrased in theory language, it's a question of what is the UV completion of Einstein gravity. So I don't see why it couldn't be that some UV completions of Einstein gravity live in number 1, and some UV completions of Einstein gravity live in number 3.
But you said only the number 2 and number 3 have evidence in string theory.
Yeah, that's right.
So why are there still people in the number 1 camp?
In number 1?
Yeah.
Well, there are theoretical models of two-dimensional gravity which seem to live in number 1, which are very well controlled, although I think maybe slightly uncontrolled in subtle ways. So there is theoretical evidence for number 1 in two-dimensional gravity. Yeah. They're all, none of them are crazy. Wait, you had a...
Oh yeah, so I was going to ask about how locality came into this first in the no small corrections argument, because I thought the first two were sufficient to imply both of the assumptions that went in, right? Why did locality have to appear separately? So unitarity and
Well, I'm going to come back to that in a minute, but basically the idea that you can have a region called A, a region called B, and a region called C that are independent regions, that was locality. And that I think is the assumption that, well, that's a loophole. That's something we could drop and maybe get out of this quandary. Yeah.
So the solution that you presented in the colloquium seemed like very elegant in that you didn't have to like, I mean, you were assuming like Euclidean path integral, but effective field theory for quantum gravity. But like the fact that it worked seemed like that should count as evidence that might move people from the other camps into your camp. Is that happening, or are they like not leaving their camps?
I would say that people have been moving from this camp skipping over that one for the most part, but moving from this camp into this one gradually for the last 40 years. And I don't think that what's happened in the last 2 years has had a huge effect on like how many people are where. But I think early on, when it was really just a general relativity calculation that people were talking about, it was much more reasonable to be up here and say, okay, information's lost into the black hole, let's deal with it. But now that, like, the better understanding we have of truly quantum theories of gravity, which started in string theory and came through ADS-CFT, the better we have those theories, the more it seems like we actually don't need to throw away unitary quantum mechanics. So I think, I don't know, at least, well, I can't tell you what other people think or why they think it, but I would say that the evidence for something along these lines has been growing steadily for 40 years, and in my view is pretty overwhelming, but it's just theoretical evidence. I mean, it could be wrong.
Didn't Hawking change his view?
Yeah, I think there's, I don't really know the story though, yeah.
Yeah, so one of the assumptions that went into this derivation of the page curve was that the initial state of the combined system was a random pure state, right?
Sorry, you're talking about Page's derivation of the page
Yeah,
curve?
yeah.
The initial state did not have to be random. The evolution had to be random.
I see. Yeah. Okay. So then, how does that apply to the black hole case? So why is it justified in assuming that?
The assumption of Page was that black holes are sufficiently complicated that you can model them by model their Hamiltonian time evolution by a random unitary. When he made that assumption, I would say it was just like a first guess toy model kind of thing. There's actually now a great deal of evidence that that's a good model. Quantitative evidence beyond just, well, there's the matching of the Page curve, but there's also other quantitative evidence that you can model it by a random unitary and get a very good answer, and there's an understanding of how fast those random unitaries act, which maybe we'll get to as the topic of scrambling. Okay, so as we've been sort of hinting at, one loophole in this problem is what if A, B, C are not independent? they are independent in quantum field theory, but what if they're not independent in quantum gravity? That is, the Hilbert space is not just a factor of the interior and these three regions. Well, then you don't, then, I mean, in some sense, then there's no problem. There's no problem at all. But of course, you need to find a way of making sense of this without breaking the rest of physics. And the other part of this is these non-perturbative effects we keep talking about. So what am I referring to here? Well, the density matrix of the radiation, and this is another way of stating the small corrections and robustness of this argument. So what is the density matrix of the Hawking radiation? Well, it has a thermal, Hawking's calculation says that it's thermal, but Hawking was doing a low energy calculation, it's not exact. So there are corrections to this. There's a series of loop corrections and, well, loop corrections, which are perturbative corrections to this. So these dot dot dots refer to perturbative corrections, and these respect the tensor product structure of the Hilbert space, HA times HB times HC. That's true even though that includes gravity. So that includes perturbative gravity. Perturbative gravity still respects the factorization of the Hilbert space into subregions. Even though you can bend light cones and stuff like that using gravitons, as long as you're working perturbatively, you can think of those gravitons as quantum fields that live on some background, and they respect the factorization of the Hilbert space. So anything that shows up here in these perturbative series is not going to fix the problem. But there could be non-perturbative corrections, which we think of as being of size e to the minus s. S here is the entropy of the black hole. So these are incredibly small. The entropy of a solar mass black hole is like 10 to the, I forget, 70 or 80. So these are tiny corrections. And you might think that they can't possibly help, but these non-perturbative corrections might be big enough. That's easy to see, because when we calculate the entropy, it's minus trace of rho log rho, which is minus the sum over the eigenvalues lambda I log lambda I. So this is infinite, this matrix is infinite, but the terms in the sum that are, the question I want to ask is how many terms are there in the sum that are actually important to the calculation of the entropy? And the answer is e to the s. That's just the usual fact that they're e to the s. At a given temperature, there are e to the s states that are important in understanding the density matrix at that temperature. Okay, so if this density matrix has tiny off-diagonal terms of size e to the minus s, those can correct the eigenvalues of the matrix by e to the minus s's. And when you add them up and do the sum and calculate the fine-grained entropy, you might be able to cancel your e to the minus s. Okay, so so the point being that these tiny e to the minus s corrections, which look completely negligible from the point of view of matrix elements of the density matrix, can actually be a leading order effect when you calculate the entropy. This is actually why I don't like to call it a paradox. I think the word paradox suggests that there's a totally well-defined, well-controlled calculation at low energies that somehow gives the wrong answer. And I don't think that's the case. I think Hawking calculated this term, and we never should have believed that his calculation was powerful enough to get the non-perturbative corrections. There was no reason to believe that. So it would have been more accurate from the very start to say that Hawking's calculation simply doesn't tell us whether the evaporation is unitary or not. Now, why didn't people say it that way? Well, because this is just wishful thinking. Because if you don't actually have some effect that produces these terms, then it's reasonable to calculate the terms you know and see that it's non-unitary. And it's just wishful thinking to think that somehow these non-perturbative corrections are going to come in and like conspire to give the answer that you wanted. But actually, I think that's probably what happens. That's probably what happens, and there's evidence that is what happens. Now, since I'm biased, I should say that, like, when I say I don't think it's really a paradox because there are these non-perturbative corrections, well, I think some of these people in another camp, say the remnants camp, would say, I agree there's no paradox because there could be remnants. Okay, so we all agree there's no paradox, but maybe we disagree on which loophole you're supposed to exploit in order to escape it, and that's why the puzzle lives on. Yeah.
Is this sort of correction something Hawking could have even calculated? Like, did they even have the tools back then to think about like the gravitational path integral and like? This is a more of a historical question.
Well, if you're talking about replica wormholes, which are only sort of indirectly getting at this, then the answer is that when Hawking first did this calculation in the early 70s, no, but by the mid 80s, the answer is certainly yes. Yeah.
How does the e to the minus s term relate to locality?
Good, because if there are because of where these would come from in the path integral. Okay, so when you do the path integral, you have some fixed geometry. Imagine you have some fixed geometry that you expand around. The expansion around that fixed geometry will give you these terms, order by order in the expansion. And it makes sense to talk about the local, so you have some manifold, and it has like leg cones on it. And it makes sense in perturbation theory to talk about like, oh, there's a region A, there's a region B, there's a region C, and if I live here, I'm stuck in region B, and you could say things like that when you work perturbatively around a fixed manifold. But what non-perturbative effects can do is they can give you totally different geometries that contribute to the path integral that just don't look anything like the one you were expanding around. And then I don't even know how to ask the question, like, where's my light cone? Like, quantum tunneling is not as simple as like, you're in this state and then suddenly you're in that state. But if we pretend it's that simple, suppose at some time we tunneled into a totally different geometry. Then what does it even mean to draw light cones? It doesn't even really make sense. So non-perturbative effects, we don't really expect to be, we don't even really know what it means for them to be local. It's something we need to understand. But in the context of black hole evaporation, or, well, let me give another example. In quantum field theory, operators commute at space-like separation. But in quantum gravity, we don't think this is true. Quantum gravity, there's e to the minus s's on the right-hand side. So locality, again, is being corrected somehow by these non-perturbative effects. The other thing that I should mention in this context is, and this has been implicit, but let me write it on the board. Is ADS-CFT. Okay, so when I described ADS-CFT, the way I described it was to say that there are some situations where you have a black hole in string theory, where if you're someone who's outside, you can delete the black hole. So this is now an empty circle, but there's a CFT living on the edge. Well, CFTs are certainly unitary. Okay, they're just quantum field theories. So CFTs are certainly unitary. And if ADS-CFT is true, then black hole evaporation is unitary. Okay, so this is part of the evidence that I would say accumulated over the years from string theory, that black hole evaporation really is unitary. If it's not unitary, then ADS-CFT is wrong. Now, you can't really say, so there's a logical issue here. You can't really say that ADS-CFT is evidence for unitary evaporation. As Maldacena himself pointed out, it would be just as logical to say that black hole evaporation is evidence against ADS-CFT. Because after all, we have calculations, like Hawking did a calculation and it wasn't unitary, so ADS-CFT must be wrong. Well, I think it's not. I don't think it's wrong, and the way that these two things are reconciled is, I think, that we just have to be very careful about what we mean by locality and quantum gravity. And in the case of ADS-CFT, there just isn't a. You can't draw a region here and call it region A and say that it factorizes from the rest, because after all, that's somehow encoded in a CFT living on the boundary. So if I'm an observer, or I'm an experimentalist who only can do stuff out at the edge, but I have a very powerful quantum computer that can manipulate the quantum state of that CFT however I please, then I could turn the knob on my quantum computer and influence region A, which is deep inside the black hole somewhere. So in ADS-CFT, there is this non-perturbative rethinking of locality. That one region of the space-time, which is deep inside, can be encoded at the edge holographically. So I think as far as the three options for evading the paradox, ADS-CFT falls under option 3. It falls under the option of rethinking what it means to be local in a theory of quantum gravity once you include non-perturbative effects. Okay. Any last questions about this?
So I thought the lack of factorization was a statement about like strengths of GR or something. You were saying it does still go through.
No, that's a separate issue. That's a separate issue. It's not the issue that I'm.
So here you just mean like there are different regions and we can distinguish them, A, B, and C. Or in the sense of locality.
Yeah, there's two reasons. There's two separate reasons that regions do not factorize in quantum gravity. One has to do with the constraints, and the other has to do with non-perturbative effects. I think the important one is the non-perturbative effects, but there are people that disagree with this. So.
We are still saying that if perturbative gravity, the Hilbert space factorizes in the superorbit sense.
Well, not exactly. It doesn't exactly factorize. So even in a gauge theory, the Hilbert space doesn't really factorize because you have a Gauss constraint that relates the two halves of a system. But basically, it doesn't get you into trouble to pretend that it factorizes. And in gauge theory, I think the same is true in gravity, but there are people who disagree with this, and it's an ongoing discussion of whether you have to worry about that. And that has to do with these constraint equations. Did you have a question, Ryan, or someone?
I'm going to ask it afterwards.
Okay. Yeah, go ahead.
Oh, I didn't understand the estimation of the order of magnitude of non-productive correction. Are you summing over like e to the s number of saddles?
No. Here?
Yeah.
No, it's just e to the s states. So say we knew rho as a matrix. Like this is just some huge matrix.
Okay.
So say we knew the matrix and we were going to diagonalize it and add up everything and calculate the entropy that way. Then at a given temperature, there would be e to the s states that matter in that calculation. And that's the e to the s that I'm talking about. It's the number of states that contribute. When we do a path integral, this is going to be, we're going to get terms like this from one saddle point in the path integral. And when I say e to the minus s, what I really mean, and the reason it's non-perturbative, is that this is e to the minus 1 over g Newton times stuff like kinematic features of the black hole, like the mass and stuff like that. Okay, so it's non-perturbative in g Newton. When a black hole is evaporating, it doesn't have one entropy. Like the entropy changes as a function of time. So I'm being sort of schematic and calling it e to the minus s. Yeah.
I was just curious, since you talked about tunneling between geometries and there's locality stuff here, is there any connection to cosmology and the horizon problem and something like inflation?
We don't know. We don't know. It's a great question. I hope so, but we don't know. There's a lot of puzzles with cosmology that are similar to the puzzles with black holes. Like there's horizons and singularities and entropy and stuff like that. But I would say we're like at least 25 years behind on applying these ideas to cosmology. Hard to say exactly how far behind, but the part of the problem is that we don't have models in string theory where things are controlled enough to see this stuff working in cosmology. So it's been difficult to develop the technology there, but maybe, we don't know.
Could you repeat that question?
What?
Could you repeat that question?
Whether there's like whether this stuff is relevant in cosmology, I guess was the question. Yeah. Okay, we're gonna move on to a new not a new topic, but a new topic next time, which is a calculation of entanglement entropy in conformal field theory. And then we're going to, so maybe I'll just tell you the plan. We're going to talk about entanglement entropy in field theory, do some field theory calculations. And then we're going to talk about calculating entropies in gravity and use path integrals for both of these. And then we're going to talk about doing calculations of effects like this from gravitational path integrals, and then it's going to be New Year's, so that'll be it. So we'll get to CFT entanglement entropy next time.